When people want to emphasize someone's extraordinary toughness, they often say that nothing can burn them and nothing can make them sink. But then, what are we supposed to say about a chemical element so extreme that even water bursts into flames the moment it merely comes into contact with it? As unbelievable as it may sound at first, a chemical element capable of making water itself ignite does in fact really exist. And fortunately for all of us, no one has yet invented any kind of device that could spray this gas through a pipe directly onto the surface of water. This element is so intensely reactive that it can only be handled using specially designed equipment made from compatible materials and passivated to resist its effects. So, what exactly is this uncontrollable element, one that can set water on fire and aggressively corrode almost every material it touches? Hello everyone! Let's reveal the terrifying secret. It's a gas called fluorine, a chemical element with the symbol F and atomic number 9 on the periodic table. Of course, every chemist already knows about this element, so in reality, it is not much of a terrifying secret at all. Welcome to our channel! Now let's take a closer and more detailed look at this cunning and dangerously reactive element. Let's get started. Why is fluorine so incredibly aggressive? The answer lies deep within the very structure of the fluorine atom itself. Fluorine belongs to the group known as the halogens, which also includes elements like chlorine, bromine, iodine, and astatine. All halogens are highly active and extremely reactive by nature, but fluorine stands out as the most intense and aggressive of them all. Inside a fluorine atom's nucleus are 9 positively charged particles, called protons, while 9 negatively charged electrons orbit around it in 2 distinct energy levels. In its outermost shell, there are 7 electrons, meaning it is just 1 electron short of achieving a completely filled and stable configuration. And this exact detail is the key to understanding fluorine's extraordinary reactivity. To reach the same stable electron arrangement as neon, a noble gas, it only needs to gain just 1 more electron. It is well known that everything in the universe naturally tends to move towards a more stable state, where entropy reaches its maximum possible level. As a result, fluorine quite literally goes out hunting for electrons, aggressively pulling them away from other atoms whenever it gets the chance. In chemistry, this tendency is described by a concept called electronegativity, which measures how strongly an atom attracts electron density toward itself. On this scale, fluorine ranks firmly in first place among all chemical elements, with a appalling value of 3.98. Yes, it even surpasses oxygen, widely recognized as a powerful oxidizer, which has a lower value of 3.44. Because of this, almost any substance that encounters fluorine is immediately at risk of having its electrons stripped away. As a consequence, that substance can no longer exist independently and is transformed into a compound bound tightly to fluorine by powerful electromagnetic forces, forming what we call a fluoride. The history of fluorine's discovery. As hard as it may be to believe, the story of fluorine's discovery was even more dramatic and dangerous than the discoveries of elements like polonium or radium. In the relentless attempts to isolate pure fluorine, dozens of scientists were injured, many of them suffering severe consequences. Because of its ominous and deadly reputation, fluorine earned a grim nickname among chemists, the martyr element. Not because fluorine itself is a martyr in any literal sense, but because it has a terrifying tendency to create martyrs out of those who study it. Pure fluorine is an extremely toxic gas, and when inhaled, it causes severe chemical burns in the lungs, along with dangerous swelling of the airways and intense poisoning. Even more terrifying are the effects of hydrogen fluoride and its aqueous solution, known as hydrofluoric acid, on the human body. This substance is considered one of the most dangerous acids, not only burning the skin on contact, but also penetrating deep into the underlying tissues. It can even destroy human bones and binds with calcium in the blood, which means that even small amounts can quickly become fatal. Historical records show that during the early efforts to isolate and study fluorine in its pure form, several researchers lost their lives, while dozens more were left seriously injured. One of the most famous victims in the quest to obtain fluorine was the British chemist Humphrey Davy, who attempted to produce it through electrolysis in the early 19th century. During his experiments, he suffered repeated poisonings and endured severe chemical burns. The work of French chemist Jérôme Neclet ended in an even more tragic way. This respected scientist lost his life after being poisoned by hydrogen fluoride gas during his experiments. In fact, even the French chemist Henri Moissan, who successfully isolated pure fluorine for the first time in 1886, could not avoid burns and poisoning while conducting his research. This renowned scientist, who later received the Nobel Prize in Chemistry for his work, managed to isolate fluorine by electrolyzing a mixture of anhydrous hydrogen fluoride and potassium fluoride. The very first grams of fluorine were obtained inside a specially constructed apparatus made from a platinum-iridium alloy and fluorspar stoppers. Before the advent of modern specialized alloys and materials like Teflon, there simply were no other materials capable of withstanding the destructive power of hydrogen fluoride. Fluorine in nature. Considering the immense effort scientists had to invest just to isolate pure fluorine, you might assume that it barely exists in nature at all. In reality, that assumption could not be farther from the truth. As we already mentioned earlier, the compounds fluorine forms with other elements are exceptionally strong and incredibly stable. In a sense, it behaves like a relentless predator, locking onto its prey with an unbreakable grip and never letting go, no matter how extreme the conditions become. Because of this, fluorine ranks relatively high in elemental abundance, coming in at 13th place with an average concentration of about 0.065% in Earth's crust. During geological processes, fluorine actively participates in the formation of many igneous and hydrothermal minerals. It also becomes an integral component of a wide variety of naturally occurring minerals. For example, in apatite, hydroxyl groups can be replaced by fluorine, while fluorite exists as a standalone mineral composed of calcium fluoride. Fluorine also plays an important role in living organisms, including the human body. For example, it is present in tooth enamel in the form of fluorapatite. In fact, it's thanks to fluorine that our teeth are able to remain strong, durable, and bright white. It's equally important that fluorine is also found in bone tissue, where it significantly enhances structural strength. Interestingly, this leads to a kind of paradox. In small amounts, fluorine helps prevent tooth decay, but at higher concentrations, it can actually damage teeth and bones, causing a condition known as fluorosis. Fluoride compounds dissolve easily in water and can accumulate in underground water sources over time. Some researchers even believe that dissolved fluorides in drinking water may explain why the residents of the ancient Roman city of Pompeii, destroyed by the eruption of Mount Vesuvius, were said to have remarkably beautiful teeth. Fluorine is also present in the universe, but despite being formed through nuclear reactions inside stars, its abundance is far lower than that of hydrogen or helium. Astrophysicists have detected fluorine in interstellar molecular clouds in the form of hydrogen fluoride and the carbon monofluoride cation Cf+. The main natural minerals that contain fluorine include fluorite, cryolite, and fluorapatite. Fluorite, also known as fluorspar, with the chemical formula CaF2, is the primary industrial mineral used to obtain fluorine. It is mainly used to produce hydrofluoric acid, which plays a key role in aluminum production and in the etching of glass. Beautiful transparent or semi-transparent fluorite crystals, often displaying shades of purple and blue, are also valued as collectible minerals and semi-precious stones. Cryolite, with the formula Na3AIF6, was once widely used as a flux in aluminum refining processes. Fluorapatite, Ca5PO4-3F, is a major component of phosphate and apatite ores, which are used in the production of phosphate fertilizers and various chemical industries. The largest deposits of fluorine-containing minerals are found in China, Mexico, Mongolia, and South Africa. These same countries are also among the world's leading producers of fluorine. The most astonishing properties of fluorine. For many people, the most shocking aspect of fluorine is the way it reacts with water. From everyday experience, we all know that water is what puts out fire and stops things from burning. That is exactly why it feels so unbelievable that, for fluorine, water actually behaves like perfectly dry firewood, acting as a ready fuel source. The moment fluorine comes into contact with water, a violent reaction takes place, releasing an enormous amount of heat. As mentioned earlier, this happens because fluorine has a stronger electronegativity than oxygen, allowing it to displace oxygen from water molecules, and that freed oxygen essentially burns within the fluorine. This unusual and extreme property of fluorine has led scientists to ask a fascinating question time and time again. What would happen if life on Earth were based on fluorine instead of oxygen? Try to imagine a world where vast oceans are not made of water, but of liquid fluorine stretching endlessly across the surface. After all, fluorine is a far more powerful oxidizing agent than oxygen could ever be. In that case, life based on fluorine might have evolved in a much more intense and energetic way than the oxygen-based life we know today. This very idea was explored by the science fiction writer and renowned paleontologist Ivan Efremov. In his short story, The Heart of the Serpent, he describes a meeting in space between a human spacecraft and another intelligent species whose biology is based on fluorine. In their world, fluorine takes the role of the oxidizer instead of oxygen. Aggressive fluorine compounds replace water, and their atmosphere is filled with swirling fluorine instead of breathable oxygen. While this scenario may sound unreal at first glance, it is actually grounded in real physical laws, which makes it especially intriguing to consider. Efremov chose fluorine-based life as an alternative to oxygen-based biology because of his deep understanding of chemistry, imagining a kind of mirror biochemistry where fluorine metabolism replaces oxygen metabolism. Interestingly, in his story, the encounter between these two chemically incompatible forms of life, which should be deadly to each other, ends in an unexpectedly peaceful way. Now let's return to fluorine's extraordinary level of reactivity. Beyond setting water on fire, fluorine is capable of destroying materials that seem completely resistant to any chemical attack. Take glass, for example, which is primarily made of silicon dioxide and is often thought to be resistant to almost all acids. However, hydrofluoric acid can easily attack most types of glass, producing silicon tetrafluoride gas as a result of the reaction. That is precisely why hydrofluoric acid is used for etching glass surfaces. In addition to glass and other silicon-based compounds, fluorine reacts with a wide range of substances, including many metals, organic materials, hydrogen, phosphorus, and sulfur. Many of these reactions occur explosively, releasing energy in a sudden and dramatic way. For instance, hydrogen, ammonia, acetylene, and numerous organic compounds can ignite spontaneously the moment they come into contact with fluorine. Even substances that we would never normally expect to burn can suddenly catch fire when exposed to fluorine. For example, powdered iron and copper will burst into bright flames upon contact with fluorine. Even more surprisingly, fluorine can react actively with noble gases such as xenon, krypton, and radon. These gases were long believed to be completely inert until the 1960s, when it was discovered that fluorine could force them into chemical reactions. Despite all this extreme reactivity, fluorine plays a crucial and indispensable role in modern science and technology. One well-known example is Teflon, a material widely used across many industries, which is made from fluorine-containing compounds and is formally known as polytetrafluoroethylene. This polymer is highly durable, resistant to high temperatures, chemically stable against most substances, and has an extremely low coefficient of friction. Thanks to these properties, Teflon is used in non-stick cookware coatings, in the production of medical implants, and even in advanced space technologies. It is truly paradoxical that one of the most reactive elements can give rise to one of the most chemically inert materials. In addition, fluorine is indispensable in the field of nuclear technology. In this area, a fluorine compound known as uranium hexafluoride is used for uranium enrichment. Because this substance can easily become a gas, it allows for the separation of uranium isotopes. Perhaps most astonishing of all is the fact that this element, which is lethally dangerous in its pure form, is widely used in the field of medicine. Today, around 20% of all pharmaceuticals contain fluorine, making it almost impossible to imagine modern medicine without it. Fluorine can increase the stability of organic molecules, which in turn enhances the effectiveness of many drugs. In the end, this means that one of the most dangerous chemical elements has become deeply woven into human civilization, to the point where we often forget just how deadly it can truly be. If you enjoyed this video, be sure to leave a like and share it with your friends. Thank you so much for watching. And with that, we'll see you again next time. Goodbye!